Good afternoon, and this is Adılay Yagıkoglu. I'm a senior engineer in the transportation group of Stanley Consultants. And thank you all for joining in. I have over 30 years of bridge analysis design experience, and I had the opportunity to work on many complex bridge projects, and notably the one project is very similar to the one I will be presenting, is the flyover ramps at Chicago Midway Airport. And the outline of the presentation will be a brief overview of the project and the bridge type investigations that were conducted for the best type of bridge structure for this particular project site. And after that, I will go a little bit more in detail the practical considerations of structural analysis of curved girder bridges. And after that, I'll briefly look at one of the flyover ramps, which is ramp B67, which is the ramp with the most curvature. And after that, I will go into minor civil analyses that were conducted to calculate the lateral response of the overall structure, including the pier stiffnesses and soil spring representation for the structure-soil interaction. And then a brief discussion of results. The project is located approximately 15 miles northwest of downtown Chicago in DuPage County, just west of O'Hare International Airport. Here, the Illinois 390 Expressway, which is also known as Elgin O'Hare Expressway, connects to the Illinois 490 Expressway, which is also known as the O'Hare Western Access Expressway. And this area is this very new, and several new ramps will be built in addition to the ramps for this entire section here. And those ramps will eventually carry the traffic and provide access to O'Hare Airport through a new terminal building that will be built on the west side of the airport. This is the plan view of these expressways. Now it's tilted 90 degrees, so north is going from left to right. So this is the I-490 going south to north, and Elgin O'Hare Expressway, Illinois 390 going west to east. And these are the four ramps. I will be discussing with you. As you can see from this picture, the ramps go over one arterial roadway, which is not shown here, but it's right here. It's called York Road, and two railroad lines, Canadian Pacific Railway and Union Pacific Railroad. And these railroads become a major consideration on the type of structure. For the bridge type investigation, 5 girder systems were considered. A typical steel plate girder, steel top girder, concrete U-Girder, concrete segmental, and hybrid part steel, part concrete structure. And typical ramp is a multi-span structure, and with the railroad right in the middle, and the York Road on the second span here. Erection and construction challenges played an important role in determining the most suitable bridge type at this site. As I mentioned previously, two railroads, they are both class 1 railroads with 40 plus trains per day, and this poses some construction issues that needs to be considered at the early stages of the project. Mainly all work must stop when train passes through within 25 feet each side of track. So, this is something very significant because of the erection and transport, all kind of construction related. And in addition to that, the boom heights of the cranes are limited due to the air space requirements. And this about keeps the booms much like half the normal booms. And in addition to that, the site is very congested. There is not enough space for crane locations, and girder storage areas are very limited. And most structures require some shoring towers for stability during construction, and then those shoring towers needs to be minimum 15 feet clear of active tracks on each side. And in addition to that, girder weight and length limitations for erection and transportation. Here is an example of, in a schematic manner, how these would work. There's very limited space in these rail yards. There are like 2-3 tracks on each side, and so this had to be considered in detail for each bridge type under consideration. For example, one typical example here for each bridge type, after the preliminary design, crane locations, how the trucks coming in with the girders, how is it going to be lifted up from the truck and erected. These were all considered in detail. This is a typical picture taken from a different project that shows a plate girder erection. As you could notice here, the girders are erected usually from the outside towards the inside, and the other thing is usually you want to put the fixed pier first. Start erecting the girders from fixed pier towards the expansion piers. That minimizes the cross-frame fit issues. So after extensive research into design, fabrication, and erection consideration, the steel curved girder was found to be the best option. Here's a picture of a plate girder being erected here. Some shoring is required because these girders, due to curvature, tend to tip over. However, the owner, in this case the Illinois Tollway, requested the further investigations to be conducted for concrete U-Girder option, and here we see a U-Girder is a concrete, very heavy sections, and it's harder to erect, and basically this is also very new in Illinois. It has been successfully used in Colorado, Florida, and a couple other Washington State and Texas for this type of ramps. But in Illinois, they're not here. It's not here yet. So the Illinois precasters need to tool up their operations to fabricate this type of girders, and it requires time and investment. And in addition to that, due to the weight of these sections, new high-capacity cranes transport vehicles required, and non-standard shoring towers with straddle bands, trunk pegs needed to support the splice points, because these girders come in pieces and they are spliced in field. Basically, a piece of the section is completed by a in-field pour, and then they are post-tensioned, so requires specialty contractors and high-quality control. So based on all these things, its detailed investigation was conducted, and then it was found too risky for a project schedule, with many construction industry challenges need to be overcome in a short duration of time. So the final decision was steel plate girder bridge. Basically, the behavior of steel girder bridges, there are two major categories of primary bending. Is due to the vertical shear, vertical moment, and vertical deflections as experienced by all bridges. And in addition to that, the curved steel girder bridges experience torsional stresses which result in warping and bending of flanges of the plate girders, and skew effects also play a role. Of course, skew effects are also part of the straight bridges, but the curved bridges can also have skew supports, so that also needs to be considered in design. Typical curved girder framing. This one with two girders. As you would notice that the center of gravity of the girder is offset from the support line connecting two ends of the girder. This creates a torsional force that needs to be resisted by the girder. Since plate girders have very small torsional stiffness, the girder needs to deform excessively to resist these torsional forces. That's shown here, and often this distortion is unacceptable, and in many cases the section will reduce its load carrying capacity, and sometimes it will buckle. And to stabilize the system, basically diaphragms or cross frame members are utilized. These connect the adjacent girders so to prevent the girder rotation. In that regard, the diaphragms and cross frames become a primary member of the system. So to look into what is happening with the horizontal curvature effects, let's consider a semicircular band section. And if we pull this section from both ends with a force T, then there needs to be a reaction in the inside to have equilibrium in the vertical direction here. So there has to be some reaction. So so then from equilibrium we can say that T will be equal to Q times R. So then if we know T, we can calculate the R. This is the radial reaction that would be needed to equilibrate this system. Now, if we look at this two girder system, now the top flange will be in a positive moment region. It will be in compression, and the bottom flange will be in tension. So the top flange, H1, the skew, in this case, there will be the resultant of the skew, which will be equal to Q times this cross frame spacing, H1, pulling the top girder towards the center of the curve, and on the contrary, the bottom flange will experience tension, so that there has to be a force H 1 equal to top flange reaction, pushing it out away from the center of the circle. So in that manner, then it could be shown that and if you take the equilibrium of these horizontal forces H1 and H2 on the other side, you can calculate a relationship between the horizontal force and this vertical shear that is in addition to the other forces. This is the curvature effect, and this is usually known as V-load. And so in the V-load method, we analyze each girder independently for the vertical loads and calculate the primary moments. And using the equation we just looked at, we can calculate these fictitious V-loads that would have to be developed within the system for equilibrium. And adding these two effects gives the final results. So it's a two-step process, and so now what happens with the diaphragms in place? So the diaphragms basically, then from the V-load equation, we can say that the diaphragm force will be md over hr, and as we discussed in the previous slide, the top flange will be pushed inside and the bottom flange pushed outside in the positive moment region. So it creates a warping of the section. Here it shows an exaggerated picture of the warping. So basically what it is that we have the radial forces on the flanges of the girder. If we look at just one girder, if we look at the bottom girder, for example, we have that radial forces due to curvature, and then each cross frame acts as a support. So basically, the flange is a continuous beam sitting on its edge, subject to this uniform load of Q due to curvature. So then the flange bends in its own plane, thus creating a flange bending, which is called lateral flange bending. And they are also termed warping normal, and this lateral flange bending will create normal stresses, compression on one side of the flange and tension on the other side. And these are known as warping normal stress. Since these lateral forces are directly proportional to the bending moment, so the radial component of flange forces are all proportional to the bending moments, and then they follow the same shape of the bending moment diagram. So previously we said we add the primary moments and secondary moments due to curvature. It's a two-step process to get the final loading on the girder, and from that we can calculate the stresses, bending stresses. In addition to that, due to the these lateral loading on this continuous girder flange, we can also calculate the stress, normal stress, the stresses due to the curvature effects. A simple equation which is commonly used is this equation here, md square divided by 10 RH. Here the m is the lateral flange bending moment, m is the primary bending moment, and d is the cross frame spacing, radius of curvature, and depth of the girder. So come back to the previous slide here. The point is that from this lateral moment, we can calculate the warping normal stresses by dividing the moment by the section modulus of the flange. So with that, now I'm going to look at the analysis of curved girder bridges. They're basically, we are all familiar with these. The line girder methods, they are commonly used for bridge girders. If it's a straight bridge, line girder methods are used, and you can design everything with these methods, and using the V-load method, you can add the curvature effects with the line girder method, as we discussed previously. And then we can use the approximate methods for the flange bending, warping normal stresses, and then with that, that's one way of doing it. That's the easiest way. But this is more, the disadvantage of this method is that you still don't consider the interaction between girders. In order to consider the interaction, we need to go to a 2D grid or 2D frame element methods. Here, in these methods, all the girders and the cross frames modeled by line elements. They are basically beam elements, and then the loads are analyzed and the moments and reactions are computed. And here the vertical depth of the structure is not considered. And again, here the approximate methods are used for the lateral flange bending due to curvature effects. And these lateral approximate methods can also be used to include stresses due to wind loading, for example, other lateral forces. And three-dimensional frame methods. These use three-dimensional beam elements. The depth of the structure is considered. Cross frames, diaphragms are also modeled by equivalent beam elements. So that is, again, these elements do not model the warping of the cross sections. So again, at the end, you need to use that approximate method to calculate the warping normal stress. One improvement to this is this thin walled open section 3D frame methods. Here, an additional degree of freedom is added. That's a warping degree of freedom. That calculates the stiffness of the girder due to warping. Basically, it's related to the section modulus of the flanges. And these frame models are capable of matching more rigorous 3D finite element analysis quite closely, and they're quite useful. However, there are some issues with composite sections where these beam elements are connected to deck with rigid links. That creates some problems, so careful modeling is required. And plate and eccentric beam methods. Here, the deck is modeled by plate or shell elements, and then the girders are modeled by 3D frame elements, and they are rigidly linked. So this model represents the depth of the structure. And as we will discuss shortly, these have a little bit better response when a skew is considered in addition to the radial curvature of the system. 3D finite element analysis methods. Here the structure is modeled fully in 3 dimensions, and usually the flanges are modeled using beam, shell, even solid type elements depending on the results being seeked. And the girder webs are usually modeled using plate, shell, or solid elements. So this is a very, very sophisticated model, and cross frames are modeled by beam or truss elements. And I guess the point is that it is, of course, going back to 3D finite element methods, is that this is a very time-consuming, very rigorous thing. And obviously, with this kind of sophistication, there is no limit how good of a model you can develop, and very accurate analysis could be achieved. But is it worth it? All that effort, I guess the limit here is the time and the schedule. These things are usually done as a final check, because most projects you don't have enough time to go through this kind of thing, and every time you cannot really iterate on the section, and every time you do that it will change. So it is very important to select the right analysis procedure for a given bridge. Here I found some important information in the NCHRP report 12-79. Here they investigated hundreds of bridges in the United States and elsewhere, and then they ran a parametric study and identified some common parameters of these bridges, and then they call it key bridge response indices. One index is the skew index, which is the width of the bridge times the skew divided the span length. So that gives you some idea of how bad the skew is. The other index is the connectivity index, IC. This given by this equation, and is inversely related to the radius of the curve and number of cross frames in a span, and a constant m. M is 1 for a single span and 2 for a cross frame. So in this parenthesis I have, like, if the skew index is more than 0.3, that creates some problems, and we'll see in a second. And similarly, the connectivity index if it's larger than 1, requires special consideration. And in addition to those, we have a torsion index, girder length index, and global second-order amplification index. These are all, it looks like I'm running a little bit behind schedule, so I will skip these things. For our sample bridge, there is no skew. It is radially supported. And I calculated using this formula, the connectivity index is 0.76. And here again in this reference investigation report, they give which kind of analysis would be the most applicable. Here C is for a curved system, S for a straight system. And 2D P1 is a 2D grid model of MDX program. P2 is a plate and eccentric beam model we just looked briefly. It's a LARSA program. And 1D is the line girder analysis. So by just looking at this and calculating these two indexes, the number 1 and number 2, you can quickly see that what type of analysis would give you good results. Here, the bending is ranked A for both P1 and P2, and vertical displacements ranked A. So that is it's a very good information just to determine the type of level of sophistication is needed for a particular bridge, curve bridge. Here, for example, if the connectivity index is more than 1, then these methods start accumulating error. So, in fact, the vertical displacements they received an F. So they lose their accuracy quickly if the so if we look back here, it is directly related to the curvature and the number of cross frames. So also by calculating this index, looking at the radius, you can determine how many cross frames you would need at each span, so that will give you an idea of the cross frame spacing. And similarly, if you have skew, in this case we don't have skew, but if you have skew, you can look at these cases with curved and skewed bridge, and then what kind of grades. If you cannot find anything in this table that would work for your bridge structure, then that means you need a real sophisticated analysis, probably a 3D model. Okay, very briefly, I want to mention the cross-frame detailing considerations. Basically, the curved girders will be plumb only in one load condition. So then, so the fabricator must fabricate the cross frames to fit in the field, and this is dictated by the girder erection loads and construction methods. So that the fabricator needs to work closely with the erector to figure out how he's going to do it, so that based on that he will detail the cross frame so that everything fits in the field. So basically there are three types of detailing. One is a no load fit detailing. Basically assume that the girders will be assembled in the field under no load condition, and that is possible if you provide sufficient number of temporary supports in the field. You can put these girders on these supports so they don't experience any significant bending, so then everything will fit nicely. And other thing is that if you don't want to use any temporary supports, then you can detail it under steel dead load only. So this steel dead load fit is basically if you assemble, erect girders without any temporary supports. And the total dead load fit detailing is usually used when none of these two things work. Then you'll have to do that. But what will not work? What doesn't work is that when you have a skew and a curve at the same time, usually then you will have some girder layover as supports. But what girder layover is that it's the twist. The girder will be twisted during erection, and that twist sometimes is significant because your bearings have limited rotation capacity. So if it twisted, then you exceed the capacity of your bearing. So to avoid that, you do detail it for the total load. However, the problem with these second and third method is that usually you would have to apply force in the field for the cross frames to fit. And these forces are usually additive to the actual dead loads, so it increases the stresses in the girders. That needs to sometimes become a design, it could be significant. And however, there is also this NCHRP report 12-79 recommends that for radially supported girders systems, the no load fit detailing is the best approach, and if there is an layover in the middle of the span, then instead of using these other two methods, additional cross frames could be employed to stiffen the girder so that the girder layover is minimized. And of course, you can always put a temporary support. So that's the recommendation of the report. Okay, now I'm running a little bit short on time, so I'll quickly go on the flyover ramp 67. Here is the bridge. It is a 5-span bridge going over the railroads, and here I guess the biggest, I'll go quickly, design specification based on the AASHTO LRFD, and in addition to HL93 load, they also have a special track called Illinois 120 track. So the bridge is designed using both of these tracks, and this track is a little bit heavier with more axles. And this is the cross section. 6 girders are required because one of the requirements here is the future decking. So the agency wants to do the deck replacement, remove 1/2 of the deck. So for the remaining half to be stable, you need to have they want to have minimum 3 girders, so that adds up to 6 girders. And the piers here, the single column piers supported on single caissons used. Here this is to minimize the impact on railroad operations, and these caissons could be, one caisson could be built, constructed in a day or two, not about 2 or 3 days. 3 days the maximum. So that's very quick, very efficient system. However, when you have a single column, single caisson foundation, these things, the pier is a little bit more flexible. So then the deflection of the pier is a little concern. And here's the, also it's a good idea to come up with a girder framing and erection plan showing the erection sequence. Usually you want to start at the fixed bearing. In this case, this is the fixed pier, and you put the outside girders first, and then first you want to go and stabilize the outside girders. That requires minimum extending it over to 2 piers, fixed pier and the next expansion pier, and then from there on you can start erecting the interior girders inward. And then this also shows the other one thing I guess to mention is that you want to put all your field splices outside the railroad clearance envelope, because you cannot put anything inside this clearance envelope, which is about 15 feet either side of the track. So by putting the splices outside, that greatly simplifies the erectors, contractors' task. So that's what was done here, and these are the locations of the temporary supports. And usually in these curved girder, plate girder bridges, the expansion bearings are oriented towards the fixed pier, and this and HLMR high load multi-rotational pot bearings are utilized. And due to the length of the bridge, also modular joint are required, and due to the radial component of the movement, swivel type joints are usually used. And I have a few minutes. I'll just quickly go through the Midas civil analysis. Midas civil program was used to investigate lateral response of the structure, to investigate pier deflections, modular joint movements, and lateral reactions at abutments. The concern here is that since the piers are very flexible, but abutments are relatively rigid, so the lateral forces will propagate towards the abutments and increase the lateral reactions at abutments, and perhaps the modular joint movements. And basically model, I'll just go through. The initial model was developed using the Wizard composite bridge girder Wizard, and this is now there are a lot of good Midas tutorials on this one, so I'm just gonna go through that real quick. I guess the only thing is that Midas also has a capability for the you can define the deck pouring sequence, and how much. Usually you want to pour the positive moment regions first and negative moment regions later. So using Midas, you can define the negative moment regions to be poured later at each pier. So it's a good, nice capability. And here's the Midas civil model developed by Wizard. Basically, I did develop this whole using the Wizard, and I added these additional elements, and also these have soil springs to model the drill shaft substructure with soil springs. And here one thing that I would like to point out is that Midas civil also have that a thin section, open element here that has the warping degree of freedom, 7th degree of freedom. So when you define the girder element here, click that consider warping effect box here. That way you will get a better representation of the warping stiffness of the system. And this is how the model looks. And this is the influence line for the live load for Pier 1. Here, and this using the live load tracker, you can locate the location of the truck that gives you the most critical reactions at that pier. And then using that location, actually what I did is that I input the axial loads as a static load case. This is for an HL93 load. As you see, due to curvature, the outside wheels have more reaction than inside gears, so you can accurately put the axial force, the wheel reactions on the deck. And also the centrifugal forces are, you can input on, apply to the deck as a element or node static forces. You need to do a little calculation, but then you can apply these. And similarly, there is also a HL93 uniform load. From the, you can tell that you have uniform load in span 1, span 2, and span 4. You can also put those as nodal loads. And then bearing orientation. Quickly you orient these bearings, you go into the elastic link menu, and you can change the beta angle here to whatever direction you would like to apply. And then these are the stiffnesses of the bearings you can input for an accurate representation of the bearings. And this is the pier reactions without soil structure interaction that was done with the original wizard model. And then this is the pier displacements with using the complete model with the soil structure interaction considered. And here we observed that due to the stiffness, the low stiffness, relatively low stiffness of the piers, the deck is very rigid, so a lot of the lateral movements are resisted by the abutments, and thus reducing the lateral movements at the piers. And here, modular joint movements. So again, we did pier reactions with soil structure interaction. And lateral reactions at abutments due to temperature loading. So a significant amount of reactions are generated. And as a summary and a discussion of results, the complete model with the soil structure interactions considered, the lateral reactions due to live load effects were distributed to all supports, and these reduced the pier deformations approximately by a factor of 2 as compared to decoupled analysis using tributary span, which is a more classical approach. You take the tributary span and then apply all the loads independently for each pier, so that the three-dimensional model showed that actually that's very conservative. There's a lot of the loads propagate to more stiff abutments, and because of that reason, the lateral reactions at the abutments increase approximately 25%. And however, the joint movements were about the same as simple calculations based on expansion length. So that and put some references. These are the publications, a very useful information. I basically had a very small amount of this available information covered in this presentation. With that, I can take some questions. I'm not sure how the time is, but I'm assuming we have a few minutes.
Great. I'm making you organizer now, so you'll be able to see in your GoToMeeting menu the questions tab. But you still have at least 5 minutes to take a look at some questions.
Yeah.
Can you see them now?
Do I question tab?
Yes, near the bottom there should be.
Yeah.
So just open that up and there's.
Oh, okay.
There's a couple questions. Yeah.
Okay.
So please read the question out loud before answering.
Okay. I can barely read it. Is there a way to expand this window? Oh, VLOAD method. Okay. The question is, did the designer compare the VLOAD method to three-dimensional analysis? In one of my projects, the VLOAD method did not produce conservative design, especially when the band cap flexibility is considered. No, we did not consider VLOAD method because at this day and age, you know, with programs like Midas and MDX and many other programs available, we use those. They are shown, especially by the reference this research report you mentioned earlier, that these 2D grid methods are much more superior to the VLOAD method. Okay, did I answer the question or?
Yes, you can proceed to the next questions.
Okay. Okay, the part of that previous question was especially when the band cap flexibility is considered. Yes, yeah. The VLOAD method will not consider any flexibility of the substructure. In fact, even the plain grid, 2D grid methods will not consider that. That's the main reason why we use Midas and developed a 3D model. That is the only way you can consider the band and column flexibilities, and even you can add the soil springs to consider the effect of the soil. But none of those other methods will give you the capability to consider the substructure stiffness. You need a three-dimensional model. Perhaps you can do it with a three-dimensional frame model, but that three-dimensional frame model may be using the warping degree of freedom, using that thin walled open section element. With that, you could probably get a reasonable response. Okay. The next question. I don't see the next question. Did I miss one? Okay, hold on. Okay. Okay. Do we need to calculate live load forces due to curvature manually? No. No, we do not need to calculate live load forces due to curvature in a 2D grid analysis. With a V-load, yes. With a V-load method, because with the V-load you need to always calculate those fictitious loads required for the system equilibrium. So when you put the live load, it will change the primary bending of the girders. So for the equilibrium you need to calculate the V-loads. But in when a 2D or 3D model is used, the interaction between the girders is automatically calculated by the model. So the V-loads are already calculated internally by the model, and the final moments are basically the sum of the primary and fictitious V-loads generated by the cross frames and diaphragms. So then you don't need to consider that. The only thing you may have to consider is that approximate calculation of the warping normal stresses if your model does not have that warping degree of freedom that I mentioned in one of the slides. That without that, then you'll have to manually calculate the warping normal stresses and add that to the stresses due to the vertical loads. Well, I thank you all. Thank you much for joining in.
There's still a few questions. Do you have another couple minutes?
Sure. Yeah, yeah, go ahead.
Oh, I think within the same box you should be able to see a few more.
Oh, okay. I see that there was. I apologize. I didn't notice that. One question is that I'm not able to see anything. Did you have that message?
Yeah, we can move on from that one.
Okay. Was Midas able to implement the Illinois 120 track as a design track, and how about the double track for peer reaction? Yes, Midas Civil has the ability to define any track configuration. Basically, you can define the axle spacing and axle loads, and then you can use that as your design track. And the double track is the same. You can put two double tracks as specified by AASHTO. You would have to basically you would have to define a double track using the same capability. For example, for HL93 you have 3 axles, 8, 32, 32 keep axles. For the double track you would have to space to put another 3 axles and put spacing, I believe it is 50 feet between the first track and the second track, and then reduce the axle loads by 0.9 to simulate the AASHTO double track condition. And then you can have a moving load case using that track. Okay, next. Oh, that was from Arsalan. Did you compare Midas results with MDX output? We did limited comparison. Basically, we compared girder reactions, and we got a pretty good correlation. And however, one thing I didn't mention, because I went over the analysis parts quickly, is that with the MDX model, you need to be careful because MDX elements doesn't have the warping degree of freedom. So when you model the MDX grid model, you want to use a coarse resolution model, because if you do a fine resolution model, it breaks the elements between cross frames, so you have more than one element between cross frames. When you do that, then the warping stiffness of the flanges is not modeled. So then your girders became too flexible in rotation and gives erroneous results for deflections. So that the same thing applies to the plate and parallel beam approach. You want to use, but I looked at that. Actually, the middle resolution also is good, because only the fine resolution, I will not recommend to use fine resolution with those models. But coarse or middle resolution is good, because you don't want, you want the beam element going from one cross frame to the other cross frame. You don't want more than one element between cross frames because of the warping stiffness consideration. Another question, were the beams essentially modeled as line elements? Any issues with rigid links between slab beam line elements with cross frame? Yes, basically the curvature is, there are no curved elements, so the curved girder is modeled as series of chordwise straight elements, and we didn't have any issues with rigid links between slab and beam elements with respect to cross frame. Maybe cross frame forces. Maybe I need a little bit clarification on the question. What kind of issue is referred to? While we're waiting for additional information on that question, I'm going to move to the next question. It says, hi Victoria, and Victoria has this question. I have a question about modeling. How do you consider the connection between pier and girder? Well, the connection between pier and girder is considered as an elastic link. I can go back to that slide here. Here is you define an elastic link, and there is, in Midas you can define the height of that link. That should be about the same as your bearing, and then you can orient, if it's an expansion bearing, you can orient it towards the fixed bearing. In this case, we had it all oriented towards this pier. And then also, I don't have there are three more terms here. I just wanted to have a big picture here, so I eliminated those. But then you can input the stiffness of the bearing here inside the elastic. So if it is a sliding bearing, then it doesn't have any stiffness, so you put 0. Sometimes putting 0 causes a problem in the solution, so it's a small number here. In this case I put 0 here, but sometimes this causes some numerical instability. So a small number may work better if you have that kind of a situation. Okay, next question is pier and girder. Are they fixed by the node? I assume you're referring to the bearing. Yeah, the bearing is fixed at the pier side, but it'll move on the girder side. That is controlled by the stiffnesses we input. So if you want it to move, then you put a small stiffness. That's what I did on a sliding bearing. Well, we did not, since we had a lot of cases, we applied the equivalent static loads to the question is, why increase the axle live load nodal loading for curvature? Does the model account for the effects of curvature? Because of the centrifugal forces, the outside wheels reactions are more than the inside wheels. So that's why we input bigger to model the centrifugal effect on the truck wheel reactions, and that's how the model accounted for the centrifugal forces. But that's not all. That's the effect on the wheel reactions. In addition to that, you also apply a centrifugal force in the lateral direction for the effect of the mass of the truck, because truck still is trying to move out, and there is a friction force in the lateral direction pushing the bridge out. So that also needs to be added as a centrifugal force in addition to the truck wheel reactions are that's the normal distribution of the vertical forces. But in addition to that, you also need to input the lateral force. Another question, rigid link would force beam to have same curvature as deck, causing high forces in cross frame since web flexibility is not modeled. Okay, yeah, that is true. That there's some that results in higher cross frame forces, makes it a little bit flexible. We did not study that because, as I mentioned, we used the grid model for the superstructure design. We did not use Midas, so I couldn't answer that question. So we did not look into that. We used Midas basically for the lateral response, total lateral response of the system, including the stiffnesses of the piers and the soil springs. So I would have to get back to you on that one. We have not studied that. We did not compare, did a very detailed comparison of the 2D grid model and Midas 3D model in that regard, with regard to the cross-frame reactions. Okay, next question is how do you calculate stiffness of bearing? Yeah, that's a very not an easy thing to do. The best thing is to contact the bearing vendor. They usually, and they will provide you with those stiffness values. It's not an easy thing to do. I experienced that it's difficult to get that kind of information from them, but some vendors do have that. They do not give that information in their catalogs, but if you can call and find the right person, you can get that information from that. Okay, next question. Were there any stability analyses done for construction erection staging? Well, here in Illinois, we do not do that. The designers usually don't do that. The only thing, and that's usually the responsibility of the contractor. He needs to get a structural engineer and check that and submit his calculations to the designer for review and acceptance. But that's how it's set up here. I think the main reason why it's done that way is that because you know, we do not know exactly how the contractor is gonna you know, erect the girders. So without that knowledge, it is very difficult to analyze for stability and erection staging. I mean, that's usually dictated by the contractor. You know what? But we did provide some erection sequence, and but for this, the erection sequence we provided, we are using supports so that the erection stability with the temporary supports is not an issue. If the contractor goes with a different erection sequence, then he's required to submit calculations. And one thing regarding the stability, usually you don't want the center of gravity of the girder and the cord connecting the two ends of the girder, the distance between the center of gravity to that cord, you want to keep it less than 3 feet. If it is more than that, that usually creates some stability during the lifting the girders as well as the transportation of the girders during the transportation. Okay, another question is not Midas account for centrifugal forces? As I understand, you consider that effect in your model for vertical force and applied lateral forces. The lateral forces is applied at what level of deck? As I know, it creates problem in model analysis. Well, centrifugal forces are usually applied 6 feet above the deck, but you can get equivalent force in a moment. And I applied it at deck level, and using equivalent force system. Basically, it is a lateral force and a overturning moment. It just takes a little bit calculation. It's a 6 foot, so. Can you please post the link where we get the PDF of this presentation? That is the final
Right.
question.
We can take care of that, and I think that is the conclusion of the questions. So thank you very much again for your presentation, and I think we can conclude it here.
Okay, thank you much.
Thank you much. Have a good day. Bye-bye.